application of some of the concepts we have been playing with a more, if you want, clear relationship to what you do as interpreter. And one of those is using the velocity as a stack analysis velocity. Then the concept of multiple, and then the concept of tuning thickness. All concepts that you are going to apply using the ray tracing principle, the wavelength and frequency principle I've been introducing you, when you interpret a stacked seismic line, when you have to basically, and to give you a flavor of how we manage with the multiple. Okay? We are going to come back several times to the multiple. Every time I will introduce you a new way of reading the pre-stacked seismics, you will have a new method coming out to reshape or readjust it. So we have to put together a certain classical question, in fact, in the second part of the exam, which we do with Nick Scofield, which I give 3 of my questions, you pick up usually 1, will be classically how would you basically cancel any kind of multiple. So what are the multiple, which methodology would you use to cancel them? We are going to see all of them in the next, basically 1 week and 10 days. Well, that's a possible, for example, question that's been given next year. I think thanks tomorrow, now that we finish the refraction way, I can start to give you the full exam that we are going to expect to have next week, and probably some of the exam we are going to have with Nick Scofield. Mostly with Nick Scofield is interpretation side. Very easy example, so it's fine. Don't look me afraid. Fine. You'll be surprised by the mark. But you'll be fine. So, the question of velocity in seismic reflection, we have already seen we got a problem with the velocity, because we don't know it. Most of the case, after the first reflector, after the first basically lithology, what's below is the unknown territory of the interpretative territory. The principle of velocity analysis from pre-stacked data, that is the application and pushing over the concept I introduced with the normal move out. I show you how we do that with the normal move out, and how we recognize some multiple with the normal move out. So now you got fresh the idea. Then the well-type principle, when you connect the word of the petrophysics that we've been studying and obviously successfully look at with the Jeff, how do you apply these kind of words when you connect to the seismic word? And again, it's a problem of velocity. So when you want to well-tie a well with the seismic, that's where to start the problem. I have to say I'm trying to give you a kind of step-by-step methodology of how you need to well-tie the well when you are basically uploading the seismics and looking at wells. Because I've been looking at some project of some of your past colleague in a kind of interesting way of doing it, or quite hilarious, that forced me to have a kind of comment in the public presentation. To me, there are boundary conditions that the physics help us to restrain, and boundary conditions that we cannot put when we are well-timed with the seismics. The boundary condition come from that the well-timed seismics, basically what we call the forward seismic modeling that you are doing when you simulate doing the convolution of your impulsive signal with your reflectivity information to create a synthetics, is so simplified with respect to the seismics that you got in front of you. The doing comparison between the two, you need to understand what you expect from them. I've seen people spending months, literally 1 month in all their projects, trying to match all single reflection. It's never going to happen, never. You can spend all your life and the result is null. The problem is to get the real reflection out of it. The biggest, the regional reflection out of it. That's another story, that's simple. Multiple gather, common point, and tuning thickness. Now, that's the first problem we got. In theory, when you work with the well-log data, you can have a velocity of any sort of things, at any sort of scale. You go megahertz, gigahertz, you can see everything. You can interpret a beautiful well-log sonics that is changing for any subtle details that is able to see. You can do a proper stratigraphy, I would say, sonic stratigraphy. You still don't know which is the porosity, probably don't know which is the lithology, but you know you see a sonic stratigraphy, so a variation of the slowness or the velocity, if you want, across it. And obviously, any sort of aspect, so porosity, how much is filled the porosity, is there fluid, is there matrix, Is there a kind of cement? Is there a pressure solution? It's going to slightly change the velocity of a mineral. So a quartz surrounded by a lot of, for example, recrystallization, pressure solution around it, is going to give you to the rocks a completely different velocity with respect to the one in which you got the quartz, the void, a little bit of fluid. This implies that when you are acquiring, basically, our sonics experiment, we are playing with a wavelength that is of the scale of the megahertz. So the frequency is extremely high. So the wavelength is extremely short. So a wavelength of the range of various millimeters or microns is going to track any sort of object that is of the dimension of the micron divided by 4, more or less. So the problem is that in reality, when we are basically playing with exploration petroleum geology, is that we are playing with the sonic clock in there, with an imaginary basic reconstruction, or if you want a core on the other side, and we have to basically try to manage and to track and to recognize, to create interval velocity from the sonic. Now, the first type of velocity that you are facing is the concept of a kind of average velocity by using the instantaneous velocity. The instantaneous velocity is classically the velocity that is instantaneously measuring the velocity of your P wave across the system. So it's a well-log, classically well-log sonic law. Representation is an instantaneous velocity moving on. The average velocity is the average velocity you want to calculate in between 2 points that you want to choose. And usually, what you want to choose an average velocity that is consistent with a certain package, assuming that the package is going to be constant in its behavior. And you know perfectly well it is not always like that. So when you enter into definition has average velocity is strongly dependent by who is using it. And which are the 2 points in between of which you want to average the velocity that you got. It's very delicate, that problem, because averaging velocity implies that you are simplifying linearly the velocity in between the system. You can decide to simplify it by using it, for example, an average velocity in this kind of carbonate here, there. You have to place basically an average velocity between that point and that point. And here the velocity is really got a kind of gradient in certain direction with a strong change of velocity in between. So it's telling you that that object is not at all a continuous, I would say, constant velocity object. But if you want to assign an average velocity, you have to take a point in there, and calculate a median value, and you can choose to have a median value that is constant, because that's what it means averaging the velocity. So we are doing a simplification to the system. The things get worse and worse, where basically you need to basically play that game for several discontinuity at the scale of the exploration. In that case, you need to average the velocity by creating a kind of artificial interval velocity layer by layer, extrapolating it from the sonic log, and then create a series of kind of new layering of velocity, in which each layer has a constant velocity, and a constant velocity in which you assign a certain velocity layer by layer. The thing gets even worse when you want to well-time that story to a reflection. The reflection now is in the scale of meters, hundreds of meters, or kilometers. So the question is, where do you start? If you start from the well log, it's more easy, more precise. It's like mapping at the scale of 1 to 5,000, and then you want to export 1 to 25,000. It works. Probably if you want to export the stuff on the 1 to 25,000 to the 1 to 5,000, then you got problem, because you need to basically start from a much more coarse dimension, and you need to go to a very precise dimension to connect with the precise dimension, and then where you start to have a huge amount of interpretation problems. So when you don't know a sonic log, and you have a well with some information about the core, and you manage, because the well has been taken properly, so the K-Bush information has been done properly, you know to place the well properly, is well timed some reflection, and then you want to extract some velocity, you will realize soon that when you are going to face the sonic law, you will have a huge amount of surprise. So how these two words are going to face each other? It's not easy. Most of the error and mistake come from the fact that when you are passing this kind of change of scale, you need to be extremely careful to remember what are the simplification step by step. So what you're losing every time you start from the well log. That is one classical example of it. Now, suppose you got a sonic log information or a check shot. Even better, a check shot. So a sonic log information at a very precise depth. You stop basically the analysis, the well log, you do the information there. So you got that information there, that information there, that information there, that information there, that information, that information, that information there. You know that that information are kind of punctual information across a gradient or a velocity that is quite complicated through the depth. Probably you got a sonic log that got an extremely precise information of that. But in case you have not, you need to connect the velocity of that one with the velocity of that one. These are the only secure points that you got in your information. Those one, those one, those one, those one, those one, those one. So you got several options. You trace kind of manually a best fit function that is passing through all of them. In that case, the function need to, in some way, need to average what's happening between. And average using a best fitting, so not necessarily through geology information. You realize the problem is that using that method is a strictly, I would say, deductive method. So you use the point, you approximate to the point, but if I ask you to predict what's happened after, you don't know. Because you don't have any point. If I ask, okay, can you predict from the velocity you got there, what is going to happen there? Complicated. Second option, you don't care about the point. You say, well, the points are good, but you know, I suspect that the behavior of the rock at the large scale, I have a behavior of the elastic parameter like that, is going to have a gradient of the velocity like that. So you predict the velocity. None of those points will probably fit exactly the velocity you got, but you can predict the velocity using a function that is a mathematical function based on physical elastic property. There is two ways of averaging the velocity. Well, one way and the other way. The other way is already an interpretation because you are assuming that the velocity between that check shot and that check shot is a velocity like that. Constant, change, constant, change, constant, change, constant, change. This is called the creation from your check shot of an interval velocity. And you are assuming that the check shot is measuring the velocity exactly at the point where you have a change of lithology. If the well side geology has been doing correctly all the job. Sometimes yes, sometimes no. But it's fine, that's what you got. So you create your interval velocity. I assure you that most of the fight within geophysical groups and engineering groups is that the engineering are not that happy with that. Because the reason is that you are strongly dependent on the check shot and there is no predictive model about that. So it's a model strictly related to the check shot, fine. But to them, at a certain point, you understand how much I can push the drill below, and if you don't have check shot below, you have to reconstruct a function that is at a large scale, a function, a predictive function. And the only way to build up a predictive function is to take your elastic properties, assign a gradient of your elastic properties, and try to expect a velocity. Linear gradient is what you do when you do the depth conversion and any sort of seismic at the big scale. So you assign a velocity like that, in which the gradient is controlled by a law controlled by the elastic wave change across the rocks. The velocity that that one is predicting at the depth is going to be quite different from the one probably you got at the check shot. But probably the mistake you are going to do, the more you go below the check shot, is going to be less than the mistake you can do if you follow strictly the function that is no linear, there is no low function of rock parameter there. It's just an approximation using what you got in terms of check shots. We are not using physics, we are using best fit of points that you got from the well log. So you got two approaches there. One is an interval velocity, the other one is a continuous gradient of it. fix in mind, it's not true that the check shot points are necessarily the more correct one. Actually, why that kind of velocity need to be constant in between? In reality, the velocity could be with a gradient, and a gradient that is can be quite, you can have quite several options of the gradient. So the simplification of the interval velocity is good, it looks like fine, it represents a kind of stratigraphical mechanic velocity, but why need to be constant like that, for example? So you visualizing velocity, even if you start from a well sonics, when you are approaching the seismic scale, is extremely common. You have to make a choice. Is it your own choice, and your choice is an interpretative choice. And you need to use some other information from the regional geology around to see, well, wait a minute, I'm expecting to have a gradient like that, then I got a salt, then I got a subsalt, and the velocity I expect are roughly that one. The problem starts when the velocity is changing laterally. Changing laterally, why? Because the geometry is changing laterally. So you have a dipping layer. So as soon as you're moving laterally, the velocity you got at that discontinuity, laterally, at the same, basically a certain distance of your offset, you are going to have a completely different velocity. Please goes your discontinuity somewhere else. In that case, you start to have problem because you cannot extrapolate the velocity laterally with respect to the point where you are measuring it. So, second question, or second aspect, is that the well log is a punctual information. Then you have to build up laterally, or spread over your model laterally, and the only way to do that is to know the geology. But to know the geology, you need to have a seismic line, a seismic data set in which someone have assumed to have some migration velocity with a certain geometry. So you are turning around in which try to find a way to solve that problem, but we never got the real solution of the problem. Because in case you got a seismic line in which they assumed a migration model independent from the well, and then you got the wells in which you got a very precise information in point, but you cannot extrapolate by using the seismic that is using a geometry that comes from a migration from the velocity model that is different from the well. So basically, that's why you spend time, people, to acquire seismic, reprocessing it, remigrate it, reprocessing it, remigrate it, reinterpreting it, and so and so. That's why in the North Sea, some place you got a kind of 10, 12 different reprocessed data set and remigrated data set. The reason is very serious, a really serious problem. The velocity problem is an extremely serious problem. Unsolved. The mathematical theorem cannot solve it. You have to use algorithm, and algorithm imply approximation, doing an inverse modeling of what you expect to see in terms of two-way travel time of arrival, but they are approximating and they are using assumption. So there is a limit beyond which the mathematics doesn't help. So there is a limit over which the interpretation is your possible solution given and assume the few data that you got. So when we speak about velocity, it's very easy to speak about velocity, sonic log, etc. But the scenario is completely different. It's a little bit more complicated. Let me give you an example of what I mean. Don't look at this guy. Well, if you want to look at it, you look at it. But for me, the crucial things is that one. Those are points in which you got real information from check shot. This is the best fitting function approximating all your basically data point from the check shot. This is a velocity that is called RMS velocity, in which you are doing averaging of the square summation of every interval velocity. This is the average velocity. And then you got the stack velocity. That is the one that you got from the normal one. As you see, that one is a velocity that you can guess from using basically your well log. The stack velocity, that is the velocity from the normal valve, is the best approximation velocity, much better than the RMS and much better than the average velocity, by far. So, what I'm telling you is that for reasons that are really related to the statistical way we define the velocity, stack velocity, despite they are completely unrelated to the wells, are often a good approximation for parallel layering of a velocity, and it can be proven every time that you got check shot, you want to compare the check shot approximating function with the stack velocity. So what I'm telling you is that in case you don't have basically check shot information, so you don't have well, the stack velocity is the best approximation with respect to any kind of average or RMS velocity, etc., etc. So that's why people used to speak about stack velocity in case they are interpreting seismic without wells. That's the word you're coming up. It's telling you that the stack velocity is the best approximation you can get in the system. Okay? So, what is the stack velocity? Well, we know what is the stack velocity, because it's the one that you need to assign in order to apply the correction of the normal move out for every single geophone characterizing your hyperbolic function. Okay? And that's where it comes from. Now, what is the procedure? We have seen how we do the difference between that one and that one. The difference that one and that one is that one. Now rewrote the tau zero. In our previous equation, we were a little bit more precise. We used to put the x over the velocity. Now we can call it tau zero. His approximation is that one. Okay. Now, if I want to rewrite the velocity in that way, that's the way you rewrite the velocity. So the velocity is dependent on the distance between, basically, the distance between the source and the offset, divided by the variation of the normal move out. This is the one you apply manually to restore this kind of reflector. So you can get an estimation of the velocity by considering the normal move out in that position there. To clarify, if you write that one as an h over velocity, you got exactly the same formula we got before. If you compare the velocity you got before, you got an h over v. The v cancelled that v squared there, so v multiply h, multiply 2, multiply the x squared. That's the solution we got on the previous difference between the two-way travel time and the tau zero. It's just now I rewrote the solution by using my tau zero and my velocity square, so that my velocity become my only parameter depending on the variation of the two-way travel time measured at the x geophone minus the tau zero. So the h parameter is incorporated now in there. I don't care about that, it's mostly the velocity. So assigning normal move out is like assigning a velocity. Okay? So, the try and error experiment that you are doing by trying to find which is the best velocity that is going to get the right normal move out, that is going to have the exactly right geometry in terms of reflection, is the way you calculate your stack velocity. How you do that? Well, is a try and error. Try and error because first of all you realize soon that first try to understand from the trace which is the exact curve of your hyperbolic function is not necessarily the most clear way. The more you are zooming it, the more you are getting in trouble. So at a certain point you decide to use a best fit of your hyperbole, but you can have a kind of, if you want, possible hyperbole approximated that one. Well, it cannot be, well, that one is passing through that, that one is passing through that, that one is passing through that. What are the difference between those hyperboles? The velocity. So only one is the correct one, and only one got the right velocity. So if you are assigning that velocity, you are not correcting basically hyperbolics conformity. If you are assigning that velocity, you are overcorrecting your hyperbole. That's what I mean. I come back to the previous two diagram there. So this is your hyperbolic function. You apply the normal move out. If it is perfect, the velocity that you got, that's what you got. In the case C, you have an overcorrection because the velocity used was too low. So if the velocity was too low, it's pushing on the other way the hyperbolic function. If the velocity is too high, that's what you got in terms of the function there. Now, that's where the multiple game starts with. Because suppose you got an hyperbolic function like that. Puff. You are a geologist, you say, yeah, it's a reflection. So the velocity needs to be bigger than 1,500 meters per second. You start to assign the velocity 1,600, 1,700, 1,800, 1,900, 2,000, 2,001, 1,002, whatever, and the result is still something like that. Ooh. something is telling you that you are applying, every time you apply a velocity big under the water, is undercorrecting, basically, your multiple. Oh, sorry, your hyperbole. So it has to be that that reflection is a multiple of the water that got the velocity, that is a velocity much lower than any rock's velocity. So basically you have to try to assign a velocity that is lower than that to get something like that. Okay? So that's the way you start to recognize multiple that are the water bottom multiple by using the normal velocity. You're right, by insisting on assigning to a water bottom multiple a velocity that should be a velocity of the rocks, you will get the result of basically undercorrection. Now, how do we do? That's a diagram from the ProMark system. What do? We got a screen, it opened a screen, the ProMark basically software, in which you got the times, and then you got a possibility of choosing various normal movable velocity to assign in order to reapply your basically to apply your various velocity in order to find the right one is going to correct properly the things. Now, as you see, it doesn't work that you got one velocity right and it works. It's a trial and error. It's a kind of density of possible velocity that need to be tried in order to get right the basically the correction. So those are your hyperbole. Those are the velocity you are assigning for a while. So if this is 2000 in the meter, well, a little bit lower than that will be 1500, etc. So this is almost water velocity. Then you start to have basically a real rock reflection velocity. So it's telling you that most of those are kind of probably multiple of the water bottom. And what you, when you assign the right velocity, density of velocity, the possible velocity, you will get most of the reflector from there to there corrected with the real geometry. I'm assuming that the real geometry is a flat geometry, otherwise normal one doesn't work. But that's an assumption of all this kind of explanation now. And that's what you got. And then you got your velocity basically model of the stack velocity model that you got by several try and error in order to correct the system. All right. So that's how you estimate the stack velocity. And we know from the previous diagram that the stack velocity is even better than the average velocity by using well. The only best velocity better than the stack velocity is the one that you got from the check shot. That one is the best you can get without any wells. So you have estimation, do an estimation using the normal move out, and so you are getting two things at the price of one. You're getting the right geometry and the velocity. Okay? So this is an example of what's happened when you do the velocity analysis. If you look at there in details, it's telling you which velocity has been applied to the whole system or reflection, which are the result. Velocity of 1,400 meters per second, water, clearly water, with low salinity, by the way, because it's a little bit below the 1,500. It corrects pretty well this kind of reflector. All the other ones are basically all a kind of undercorrected. So you need higher velocity to get those ones. In fact, in theory, if you move to 1,400, 1,500, you should correct the ones below better, those ones, and you should basically start to overcorrect, the more you go to a higher velocity, all the ones that were correct at 1,400. And the more you are high in the velocity, the more you are going to be able to track which are the rocks that got the velocity of 1,600, 700, 800, 900. So you can locate the velocity distribution or stratification of your system. Now, have you seen what's interesting is that at the depth, below clearly real rocks, it has been undercorrected by assigning the velocity of the water. Much below, you got some reflectors that are perfectly parallel at 1,400 meters. That is telling you that what the hell are they? The only way to get a velocity, a reflection so deep with the velocity of water is to have a multiple that has been traveling a long times in the water bottom and has been registered and assigned in terms of two-way travel time arrival in an erroneous way as a reflection with the velocity of the water. So this is the way you can track multiple during the pre-stack analysis of the velocity. So this is a multiple, you know it. That, so in theory, if you got a wells at that position, the reflection doesn't exist. Okay? Move on. You will start to assign velocity of very high velocity, so you can start to track. So those are the reflectors that got 1,600 velocity. Those are the ones that got the velocity of 1,700. So you see there are several reflectors nearby each other that are reflecting various different velocity, but you got those reflection to reflection. That one goes 1,600 meter, 1,700 meter, the 1,900 are positioned in there, the 2,000 meter per second are positioned in there, and then you got 2,300 positioned in there, in there, in there. Okay? So, assigning a stack velocity using the normal move-out method help you to recognize reflector by reflector, to assign reflector by reflector, which is probable geophysical velocity in the system. So you are creating what? You're creating a velocity model. From the velocity model, once you got the stack velocity, you can assign a certain average velocity for a certain thickness, time thickness, because the layer that got basically that velocity are those one. That one is the one that got the 1,700. That one is the one that got the 1,900. So, what you do, you start to use the stack velocity to assign a certain interval velocity and to create your velocity model and your stratigraphical potential information if you got piece of core or other information from other place that allow you to recognize the reflector. So you use the stack velocity to create an interval velocity system. So you create a stratigraphical interval velocity using the stack velocity. That's what basically allow you to do the geophysics without the use of any wells and without the construction of a real complicated velocity model by using 2D line. And you do that for several 2D lines. Now, what is the reality of the problem? That, well, you realize that if you play seismic by seismics in a 3D seismic data set, it takes time, it's a tedious experiment. But you can start to build up a proper, I would say, surface of velocity variation in doing that. 2D line, 2D line, 2D line, 2D line. And the variation of the 1,600 velocity is going to represent a surface with a certain orientation. The 1,800 is another surface like that. So you create a kind of morphology of velocity. You can create in 3D a velocity model. And you can use that velocity model to then run or give it to a seismologist, so geophysicist, to run his forward modeling to see what you should expect to see in terms of geometry. If it matches with what you got in seismics, and then the real proof of everything, all of that, the real proof of that is when you go back to the manager, look, I'm going to see if you are right or not, I'm going to do a kind of drilling to understand if it matches. And then you have to pry that match. If it doesn't match, well, for a drilling, for a velocity model, that doesn't work. So, okay, so that's the way to work from the pre-stack procedure using. Have you seen, the only thing we are using in all that story is the concept of normal move-out that come from the concept of ray tracing, that come from the concept of a pure trigonometry approach of the seismics. No else. Okay? Now, what's happened when you got check shot and wells, and you want to compare it with a seismic that is a stacked seismic, in which probably you got some stack velocity from the geophysics behind you, because you need to stack basically the data set, so you need to use a stack velocity during the pre-stack processing. How do we use sonic density well log to generate a synthetic seismic trace? And the synthetic trace is compared to the real seismic data collected near the well location. Let's start with the boundary condition. What we got from the seismic data, what we got from the well data. What are the boundary conditions that define the well data and the seismic data? Seismic data usually got low frequency, between 5 and 60. It can be 5 and 200 Hz. With the broadband, you can write, instead of 60, you can write 200 hertz. Okay, this is the most dramatic difference, but it can be 200 hertz. Well, 200, no, 180, 150, something like that. In any case, very far from the 10,000 and 20,000 hertz. So you are comparing basically, I don't know, okay. From a geological point of view, you are comparing a single granule of the sandstone you got on the beach with a big olistolith that you got in the Alps of several hundred meters. That's the definition of what you are comparing in terms of gains. In fact, the vertical resolution of one is between 15, it can be 5, 100 meters, and the 2 centimeter, 2 meters. The horizontal resolution is even more dramatic because the horizontal resolution is much more complicated in seismics. And in one case you are measuring amplitude, phase, continuity, horizontal, vertical velocity at best. Another way you measure a lot of fancy things that you all know. So you can measure vertical velocity, density, resistivity, reflectivity. So you got a huge amount of data, punctual data, instantaneous data, compared with an object which is a kind of rough, kind of observation of the system below. So that's the way you compare those objects. So when you want to do a well tie of a well, you need to decide how much you expect to well tie and what you want to well tie. Clearly, you hope that a peak with a peak will work, but not necessarily like that, because one peak in there has a kind of definition of several millimeters. The other peak here is a definition of several 100 meters. Now, what is the theory behind? Is a theory we are going to see more in details when we do again the processing side, but this is a good introduction. We know, I'm pretty sure you know from Jeff lab, that lithology can be expressed in terms of contours of impedance, and the contours of impedance we have seen that is velocity multiplied by density. You can have a velocity model from the sonic log, you can have a density model from basically well log information. Okay? So you can create your impedance basically model, so your reflection coefficient or reflectivity model from that. Something we have been doing as an exercise a couple of days before. Remember, you can extract. So what you need to do is that when you got your reflection coefficient, you have to do a convolution, so a multiplication against a kind of numerical value that approximate your wavelength, that should approximate your source. Usually you got several type of wavelength, you got a Butterworth wavelength, you got a Ricker wavelength, etc., etc. All wavelength with different, slightly different properties. All of them need to be zero phased. I need to store most of the energy into the big part of the peak. We are going to see that in extreme detail when we do the processing stage of that. Or we can distinguish instantaneously by looking at wavelets with a certain amount of frequency, with a certain distribution of noise around, in a spectrum analysis of this kind of thing. It's very easy. No math is required. But what you do when you do the convolution, you recreate a possible synthetics and a possible information about it. Now, what is the problem? The problem is that when you got the sonic has an extremely detailed information about that. It has an extremely detailed density variation of that. So you need to recreate your synthetics thinking at the dimension of the seismic. So you have to choose a certain point to put limit between the interval. What you got in reality is that you got often software in Petrel, in Kingdom Suite, that does it for you. But you have to tell him some kind of boundary condition, and what you have to basically touch the information is when you are telling him which is the windowing in which you want them to sample the information of the lithology from the core of the velocity from the well. Because if you let him do it properly and systematically, you will have an extremely precise synthetic recreation of all sorts of basically amplitude that you are never going to see, they are never going to match with the seismic because it's completely out of scale. So one reason is that one problem is to choose and to tell to the software what is the blocking windowings. The blocking window is in which you tell to the software how you want to choose or to pick up or collect or sample the continuous information from the log and the sonic log that you got. Remind that you can have three options. You can have an option in which the sonic log is as complete as the density log. You can have the situation in which you got only bit and piece of the sonic log and a continuous density log, and the way around. So, again, when you are sampling one, if they are not with the same continuity in one respect to the other, you have a problem that some blocking windowing is going to be completely empty. And that's something you don't want. So you have to assign a value. So you have to tell to the software, yes, if the window I'm choosing have the mistake or has the unlucky situation, it is sampling an area where there is no solid information, fill it with a medium value calculated from the less information and the next information. So you are creating an artifact. The best thing you can do, we are creating an artifact. So that's what I mean. You got the continuous sonic log, the continuous basically reflectivity information. If you map basically sample like that the information, so you have assuming that that peak is basically spread over that distance, and that information basically in there is assigning that peak to all that windowing, and then you do the convolution of the sampled basically information from your well-logged sonic. You do the convolution with the wavelength. That's the whole possible wavelength that you can get. It's not easy. And that one is going to be different from that one. It's going to be different from that one. Slightly, but it's going to be different. So that is the stage when you are doing your basically well-logged calibration. I literally think about, because this is the most delicate step, is the blocking, choosing the windowing, sampling of your sonic log well-log that you upload in your seismic dataset, because it's going to affect terribly the way you are going to produce the final synthetics during the convolution. So suppose that you decide that you find a kind of blocking window, you find out, produce the synthetic wavelength by doing the convolution, the software did it for you, and you got basically your synthetics assigned to a wells. Well, if everything is fine, sometimes it's not, isn't it? Sometimes it's not very fine. If you don't know the K-bush and the location of the coordinate of the wells, it's complicated. Then what you got basically, you need to be sure that the coordinate you are assigning your seismic synthetics experiment is the one related to the well to which you want to assign it. And hope that the K-bush information you got from the wells is a correct information, so you are going to start exactly the point is located with the K-bush, or with the first information respect to the K-bush that you got from the well. Good luck. You do all of that, and you realize there is something that doesn't work completely. Oh, better. You realize that there is a kind of similarity between your synthetic, basically, that you are uploading, and the seismic that one, and that one, they should be there, there, and there, isn't it? That one is getting there, and that one, it should be there. Oof. So Clear is telling you that probably you didn't get wrong with the synthetics, but you get something wrong from the location of the K-bush or the distance of the first information where you decide to use the first density in the first sonic log respect to the real top of the line. Now, one thing that you should not do, you should never do, if you do that, you've got to get in trouble. You should not do it. Don't do it. Forget. Cancel from the mind. Is to do a distortion of the synthetics. Don't do that. The only thing you are allowed to do, but you have to explain the motivation, you have to find out why you can do it and you should do it, is to translate laterally, but translate without touching the synthetic. You just shift. Your shifting doesn't change the relative frequency and wavelength of the synthetic. So the synthetic is preserved, but you can shift it laterally. To shift laterally, you need to find out the motivation of that. The third thing to do that is that you go back to the information of the well log, and you compare with the PDF of the description of the core that has been described by a well site geologist. And you're going to see if the K-bush information you got, you uploaded as a kind of well data information, is consistent with the description of the PDF. So if the real first information which you are assigned to density is at that depth, as it is described by the website geology, if there is a mismatch, probably it's going to explain you why the K-bush has been, by mistake, uploaded as a kind of K-bush. You never know what's happening between when you're measuring that in the field and then you are transferring the data to someone else to upload it. But if you got a kind of mismatch, it's telling you that you can shift the object. So what you can do something like that. You shift it, then it works. It works kind of. Same story. The position of the K-bush is laterally. Sometimes it doesn't. They don't really give you an extremely precise position. So it can be plus minus 10, 20 meters. Okay, plus minus 20 meters means that you have a kind of space to play with that. The reason I'm telling you is because that one is okay. That one is not really there, but you realize that the strong amplitude of that is changing laterally. That one the same. Probably if you transfer laterally, it's going to work. And those two wavelengths, that's something that you cannot do anything, but clearly they are approximate, they represent the real big tick object in there. What it's telling you is that the precision you imposed when you did the windowing in your synthetics is not basically what you find out in the real seismics. And probably those two wavelengths is registered by the geophone as the single wavelength, but really fat amplitude. Another thing you can do is to shift laterally the system, and then it starts to work out, kind of. Now, as you see, not all the reflectivity are matched by the synthetics. And I assure you, it never happened that all the reflectivity are matched by the synthetics. And the reason I'm going to see that in the hand, but for the same reason of the boundary condition I told you before, but also of the assumption with which you are running your experiment of your synthetic. Your synthetic experiment is a convolution, so you are assuming that your basically amplitude is created by a perfectly orthogonal ideal experiment going through the rocks. While the seismics, you have transformed it with the normal move out, but the original amplitude has been tracked by the geophone at different inclination and incident time. And we know from the equation of the wave that as soon as you have an incident angle, it complicates a little bit the way it distributes through the change of mode through the transmission of the wave. So the amplitude you're going to register are going to be clearly a little bit, slightly, or even a lot different from what you see in the synthetic. It is an extra super simplification of the real experiment.
So just quickly, going back to when you're shifting the synthetic data, can you shift that? Or so you're saying laterally, can you do it vertically as well?
Yes,
yeah.
within the distance that is the distance of error of the location of the K-bush. So the K-bush is telling you, well, the position is that one, plus minus 25 meters, 100 meters. That's what you can play with. Oh, the K-bush is the position of the top of your well when they are giving you the well information on that. When you upload the well, you have an information which is the top coordinate system of the well. And it tells you in meter where it is with respect to the seabed, with respect to the water, or respect to the position that is a reference system. It doesn't necessarily match, well, sometimes what is described by the well site geology when it starts to describe the core or the cutting when they're coming out. And it's telling you which kind of position of the core he has been describing while in the information. If you find a mismatch, well, that's probably going to affect your synthetics.
Yeah, well, isn't vertical. Yeah.
No, if it isn't vertical, it's more complicated.
Yeah, but testing can be there.
It's much more complicated. Because if the well isn't vertical, you need to assign an artificial dipping orientation to your synthetics, but it doesn't correspond basically to the way you have run the sonic log across the well. Because if the well is basically dipping, the sonic well is trying to shoot the seismic at certain orientation. Certain orientation is going to produce some wave, as you know, with a certain inclination. So a change of mode, so the energy you're going to register are not the one perfectly orthogonal. So synthetic in a kind of dipping well, it takes more times. So let's stay with the simple one, Because, well, the first thing I suggest you in order to well tie the seismics to use vertical well. Start with the vertical well. Because if it doesn't work with those ones, it's never going to work with the deeper one. So start from the simple. Okay? Now, what you can see is that you can match the bigger reflector. So you can match those one, you can match those one. You don't match necessarily all the other one. Still, that's what I expect. I think it's normal. So when you want to well tie the seismics with the synthetics, look at the regional scale reflector. Those are the regional scale that you want to well tie to be sure at the regional scale. Don't look at the small object in between, because those one, they come from the necessity, they won't well tie. The well tie, if you speak with the geophysicist, is going to be the well tie by chance. So that's the way it works. So what you want to see is that you want to see the strong reflection. Strong reflection usually are the ones that separate the source rock from the main reservoir from the basically top of the reservoir of the seal, etc. etc. Where you expect to have the strong component impedance. And you want to get the regional one. Why? Because you want to well tie the principal reflector and then allow you to map all across the 3D seismic dataset, all across the 3D line. There's no point of well tying a reflector and then it's going to disappear after 100 meter lateral. So you want to well tie to be sure that what you're describing in terms of stratigraphy of the reflector, the regional one, that then you want to map, extrapolate when you're doing the mapping with Petrel or with industry. So for me, that's the game you have to do with the synthetics. Unless you want to do a petrophysical experiment, but then you are playing and working only with the core and with the synthetics. Seismics, too big scale. Assumption for the synthetic well ties. When you do the synthetic well tie, you are assuming that the seismic data are noise-free. And that's fake. It's true. It's not true. There is no multiple. So interesting things is that sometimes what you find out is that if you don't see at all some reflection you see on seismics from the well log and the synthetics, it's not necessarily because you did something wrong. It's probably because those are multiple, and the multiple doesn't exist in the core. The core, at the frequency you are playing with, doesn't create real multiple of that scale of the seismic. So if you have an extra reflection in seismic that you don't see at all sometimes in the core, sometimes there can be intra-bed multiple that the core telling you doesn't exist. So the core helps you to unravel part of it. We assume that the relative amplitude are preserved. That's true when you do the well-log sonic information. It's not true when you do the seismic, because it strongly depends on how you are processing the seismics. Remember that the well-log experiment is a zero offset experiment. The seismic is not. The seismic is migrated to represent a zero offset section, but is the amplitude when you do basically the normal move out is not preserved. That's something we are coming back to. I didn't tell you when we do the normal move out, in the frequency domain, you are applying, as soon as you do the normal move out, so you do the simple trigonometric operation, you are applying a distortion of the frequency and of the amplitude of the hyperbolic trace that you are moving through the normal move out. So you are changing the real relative amplitude information of it. The more you apply the normal move out, so the more they are larger the offset, the more you are basically interfering with this kind of properties. Synthetic seismogram. Well, the plotted logs representative of the Earth sampled by the seismic data. That's an approximation. Remember that your input data were a windowing, a sampling of the full continuous sonic log at density. So the way you choose the window is going to affect the information we're going to get in terms of the interval. Okay? So maybe sometime, if it doesn't work properly, you have to go back to your synthetic and re-sample with a different window and try to see if we can take it properly, take it right in terms of the reflectivity. Probably you miss some strong reflectivity because during the sampling, the windowing, you just choose wrong the window, and some of the window just basically went in between the peak and the trough of a strongly important regional reflection, so it's missing it. Normal incidence reflection coefficient, that's what you assume when you do synthetics, and we know in seismic it's not like that. They are not normal incidence, they are inclined incidence. As soon as you got a zero offset and non-zero offset, you need to have inclined reflection. The multiple are ignored. Rarely there are very few software that allow you to reproduce the multiple. You assume that you don't have any transmission losses or absorption. Now a lot of software of the synthetic, they allow you to take into account the spherical spreading. So make sure that you are taking the spherical spreading. Spherical spreading, remember, is the way the density of the energy of the P wave that is moving far from the source is redistributed across the front of the wave. So a wave that is far from the source has a higher density energy. The one very far from the source you have to take that as an option when you calculate the software to assign the spherical spreading. Or the amplitude are going to disappear. You are assuming that is in isotropic medium. And we know that is the size, the stratigraphy is not necessarily isotropic medium. So, putting all together, if we got error in the seismic line, basically, well calibration through the well of the seismic, well, it's fine. It's what you should expect to be. What you want to make sure is that you want to get right the large, strong, important contrast of impedance reflector that has an importance at a regional scale. The reason you want to well tie the seismic, you want to be sure that you know exactly where it is located, that regional reflector, what is his name, what is his density, information, and possibly age. And then you can start to map the seismics. Or the smallest kind of reflection in between, well, you can play with it place by place, but don't extrapolate that to the whole seismic, because some of them as reflection within that you see locally, they're going to disappear. You're never going to see them, because maybe it's a pinch out, maybe it's a local discontinuity of a lateral variation of your stratigraphy. So it's like, you are mapping geology, so you got all the problem of the lateral variation of the fasces. Okay, so is the pen, which is your basically assumption and scale in which you want to play with your well. Remember that you got some kind of log data quality problem, because the drilling fluid invasion affects them as well as your core. And so the density that has been probably calculated in the core during the drilling can give you a reality and information about the density distribution of the fluid that are not exactly the correct one. I know that there are ways of correcting it, of balancing it, etc., but that's the problem you got. Seismic, we already know the problem, which problem we got. So it's the noise, multiple amplitude gain, migration, etc. Polarity, frequency, and phase. Again, try to get it right, the polarity. If you don't get right the polarity, it means that in some place the velocity has been assigned by the well are not exactly or correctly located by the windowing that you choose. We have to go back and re-choose the windowing and reapply basically and sampling of the current of the well and retry and rerun basically synthetics. All the rest we've been looking at is stuff we have been through step by step during the well time. Now, let me jump out from the common midpoint stuff in there, stuff from tomorrow, and let me go in an easy topics. We go back to the part before tomorrow, because otherwise it's too long. But at least I can introduce you as it is strictly related to the normal Bouvard exercise, the concept of multiple. Then we will do a reappraisal tomorrow, okay? And maybe tomorrow we can spend time on doing the exercise I've been giving to you yesterday. The blackboard. Right. Multiple definition. Any event in seismic data that has incurred more than one reflection in its travel path is called multiple. Easy peasy. Due to the fact that they really represent reflection, or hyperbolic path, often they are mistaken as primary events, so now we start to introduce terms. They will be often used within petroleum company. Primary event from what we call multiples. And wrongly positioned in the seismic stacks. Look how the zoo of the multiple is beautiful and variegated and fantastic. It's people that spend all their life to explain the theoretical behavior of the multiple, to predict mathematically how they work, and to try to help or to basically cancel it. Okay? So it's a big work. The first one is the water bottom. The second one, oh, maybe let me show the diagram. I have the diagram with the real name as well of the things. Here it is. Yeah. Then I come back. Don't worry. Water bottle are those one. Peg leg, multiple reflection variously defined by different authors, but basically I find out the most important, they undergo reflection in the sedimentary sequence and all the other reflection at the near surface in the water. So they start there and then they end up stacked and trapped by the water. And then the intravert. Easy to recognize and save. Kind of easy you are going to see to recognize, some case and cancel. Those are the problem. Go back. Yeah. First, suppose we are offshore, and suppose we got, this is the water, we got the source within the water, air, water, rocks. Now, that one is fine, it's a source, it's going down, penetrating into the rocks, reflected, being registered, primary reflection, everybody's happy. That one, because remember, when you are shooting with the source is shooting at 360 degrees. It's not a polarized source. So you got ray going in that direction as well in that direction. Now, what do you think is going to happen to a reflection that is going to water to air, and then reflected back? There's something more important about that. When you got a medium, rho 2v2, that has a higher velocity that, oh sorry, rho 1v1 that has a higher velocity than the one below, rho 2v2, what you got in terms of factors of impedance? You got it? So you got a change of polarity. Yes. So every reflection that go up and then come back is going to basically store as an information a change of polarity amplitude. So what you need to do, you need to be able to track which kind of the multiple that for you they look like suspicious, and this one look like suspicious. Why? Because it starts on the water. Then it's going to penetrate on the rocks, but then it go back to the water again. So he has a velocity that is a kind of mixed velocity between water and rocks, but it has a polarity that doesn't fit with the polarity you expect to have from the really primary reflection. So that's a good signal. I would say that, well, let's go ahead. Near surface multiple are all the multiple based in peg leg, if you want. It's the peg leg. And those are the ones that start as a normal reflection, then they end up trapped by the water. They change polarity every time they reflect to the water, but they start to have a very low velocity. Long multiple paths are the ones that are reflected multiple times intravert, and so they got normal velocity with a normal polarity. So it's very hard to recognize that. Watch out, the second information that you get from the multiple is that they are traveling quite a lot. They are multiply reflected, so they are spending time across the rocks before getting registered to the geophone. So, by the time you are exploding the source and the time is going to be registered by the geophone, you will have to wait a certain amount of time. So we are going to position the apex of the hyperbola of your multiple quite deep in times. As it is equating, you are going to necessarily misposition the real reflection, the reality were happening almost on the near surface. So that's the problem with the multiple. Sometimes those kind of reflections are called ghosts. The one that change polarity and they are reflected on top of them, they are called ghosts. Now, let's stop in there. In any case, we are going to play with the multiple later on. Just a final comment. A reflection, a multiple reflection, respect the primary reflection, is reflecting several times along more or less the same unit. Now, you know that every time we got a reflection that is reflecting through in discontinuity, the physics is telling us that it's split into 4 components. is splitting across a reflected P wave, a change of mode of S wave, and transmitted P wave, a transmitted basically S wave. If you consider the very, very simple case in which the multiple is just orthogonally reflecting, you got still a transmitted and a reflected. So suppose you got a wave that is reflecting too much times and getting trapped along this kind of layering. And which kind of energy do we expect to have when it's going to be registered by the geophone after a while? You should expect to see a very low energy, because every time it's reflecting, it's losing through the transmission, the part of it, is retaining part of the reflection energy. And that's true for every single reflection. So if reflecting twice or 3 times more, 4 times more than a primary event, maybe we'll have a velocity that is the same velocity of the primary wave, but for strange region, for those regions, you will have a strange energy and so frequency. So you understand that most of the game of the multiple cancellation and attenuation is going to be played into the frequency. So again, we come back to the problem of transforming our seismic time offset into a second part of the frequency. Frequency is nothing on the other more. Okay, we'll see you tomorrow. Have a good afternoon.